Good afternoon, everybody. I welcome you all to this special seminar on localization and chaos in isolated and open quantum systems. Today we have with us Professor Manas Kulkarni from ICTS Bangalore. Professor Kulkarni is one of the very active young scientists in India, and he has a stunning academic background. He did his master's in physics at State University of New York and completed his PhD in the same university. He carried out his first postdoctoral studies at University of Toronto, Canada, and the second at Princeton University. He started his career as an assistant professor of physics at City University of New York, and then he came back to India and joined as a professor at ICTS. He has won several acclaims in his academic career. To name a few, I'd say he won the Ramanujan Fellowship, the Indo-French Joint Grant by CEFIPRA, the Serb Early Career Research Award, and the Rutgers Global International Collaborative Research Grant. And very recently, he has been identified by DST as one of the 75 scientists under 50 who are shaping today's India. I guess this is a very great honor. Congratulations on that, sir. He works in several areas in physics, not only in nonlinear dynamics, but also in condensed matter physics and statistical physics. The list is very large, and in a broader sense, he works on open quantum systems, non-Hermitian systems, low-dimensional systems, integrable systems, field theory, and mathematical physics. He has a very large number of collaborations both in India and abroad. He has made contributions to open quantum systems, which are very important from the perspectives of both fundamental science and future technologies. And I guess today's talk is going to be around that topic. Professor Kulkarni is the third visitor from ICTS Bangalore to our university. Earlier, we had Professor Abhishek Dhar and Vishal Poisson come here. And when we invited Professor Kulkarni to visit us, he immediately accepted the invitation despite of his busy schedule. Thank you so much, sir, and over to you.
Thank you. Good afternoon, everyone. Thank you so much for this invitation. It is very nice to be here. And thank you for the introduction. I'm very happy to come here to this very nice place, and have been enjoying my day so far. And I'm looking forward to speaking with more of you. So I'm going to speak about localization and chaos in isolated and open quantum systems. So I'm from International Center for Theoretical Sciences. I don't know how many of you have been there in Bangalore, but I would really invite and encourage all of you to sort of try visiting ICTS Bangalore. It's a very nice place for programs, discussion meetings. There are like summer schools and opportunities for students at various levels. If you go to the website, you will see that, especially for the kind of topics you are all interested in, there are plenty of activities going on in ICTS, and I hope to see all of you visit us in Bangalore. Okay, so I'll try to say a few words about this topic here, and please feel free to ask questions. And if you, even if we don't manage to complete the talk in the 1 hour, it's okay. I hope we will be covering as much as possible. So I'm going to speak about chaos and localization. More broadly, chaos and regular behavior. Okay, chaos and non-chaos in quantum systems, which are of two types. I'll be speaking of two kinds of quantum systems. One is closed quantum systems. Another is open quantum systems. One is Hermitian quantum systems. Another is non-Hermitian quantum systems. Okay, so isolated quantum systems. So for students who have taken courses in quantum mechanics, most of the time you are dealing with isolated quantum systems, where you have a couple of degrees of freedom and like a harmonic oscillator or some coupled harmonic oscillators or some spin system and so on. And today I'm going to speak of some such isolated quantum systems, which as you know is Hermitian, you might have studied Hermitian matrices and so on. So I'll be speaking about isolated quantum systems and its connection with random matrix theory and one-dimensional Poisson distributions. So I'll explain these words. You don't need to worry about what these are. So isolated quantum systems and their connection with Hermitian matrices. Okay, so if you have matrices which are Hermitian, I'm going a bit slow just to make sure that at least that most of you will understand the presentation. So I'll be speaking about Hermitian random matrices. The next part will be non-Hermitian quantum systems, open quantum systems. So what happens when you have quantum system which is coupled to environment? Let's say you are interested in some experiments, you can never make a perfect quantum system, right? So you'll have some leaky mirrors, some dissipation. But how do you incorporate dissipation or friction in quantum mechanics? Okay, so in classical mechanics we have one way of understanding friction and so on. Quantum mechanics, how do you incorporate? So that is open quantum system or non-Hermitian systems. And I will connect them to something called non-Hermitian random matrix theory. Okay, non-Hermitian random matrix theory. Matrices which are non-Hermitian. Okay, so most of the work I'm going to present will be in these 4 works. One we are writing still, and it's been over a couple of years in collaboration with Abhishod, who is now at Oxford. He was at ICTS before. Jed at Rutgers in New Jersey. Mahavir Prasad, who is my student at ICTS. Camille Aron, who is my collaborator in Paris. Saumi Ghosh, who is a postdoc at ICTS. Sparsh Gupta, who is a student at ICTS. And Hari Kumar, who is a Cefipra postdoc at ICTS and Paris. So now let us go slowly. So let us start with a simple problem. When we have real eigenvalues, okay. So if you have Hermitian matrix, some Hermitian matrices, let's say 100 by 100 Hermitian matrix, you will have some real eigenvalues. Okay, so you'll have 100 real eigenvalues. Let us say that they are distinct eigenvalues. So make a 100 by 100 Hermitian matrix on your computer and calculate its eigenvalues and label it E1 to E100. Okay, so you'll have 100 real eigenvalues. Suppose I have list of real eigenvalues. Okay, what are the quantities that I would be interested in my talk? I have 100 real numbers. Okay, so one quantity I'll be interested in is called level spacing statistics. This is nothing but, let's say I have 100 numbers and I calculate the gaps. Okay, and let's say I have like 500 such samples. So I will make a list of all gaps and I will calculate the distribution of gaps. Okay, is that clear? So I have 100 numbers. How many gaps will I have if I have 100 numbers? 99 gaps. And now I have 99 gaps from one copy. Let's say I have 500 such copies. I have 99 times 500 and I will make a histogram of distribution. Okay, that is first quantity I am interested in. That is called level spacing statistics. So here my eigenvalues are real. Okay, so let us understand all these quantities and then I will talk about matrices and Hamiltonians and all. But even after some point you stop understanding, it is still okay, because at least for some time you will understand most of the things. So let me next go to adjacent gap ratio. This is another quantity. Adjacent gap ratio means I am going to calculate minimum of adjacent gaps, okay, by maximum of adjacent gaps. So I have 99 gaps. Again, I am going to compute what is the minimum of all the gaps divided by maximum of all the gaps. So these are some quantities which are useful, and these quantities actually help us understand chaos. Okay, I will bring the connection later. first you can just understand in terms of eigenvalues. Okay, this is clear. Adjacent gap ratio. Okay, so minimum of let's say 7th and 8th gap by maximum of 7th and 8th gap in your entire list of eigenvalues. You have 100 eigenvalues and I have 500 such copies. So I have 100 by 100 matrix which gives me 100 eigenvalues. I have 500 such matrices. Okay, that 500 such matrices you can think of them as samples. Sample 1, sample 2, sample 3, sample 500. Okay, so please stop if you have any question, just stop so that yeah.
So your delta is just the difference or it's a delta?
This is literally gap.
Yeah.
So difference between say 7th eigenvalue and 6th eigenvalue. So delta 7. When I say delta 7, I mean just 8 minus 7. That's it. Okay. Okay. So this is basically, if I give you so many list of numbers, what all information you can get. See, some of the most basic information would be mean of all the numbers. Okay. But huh? Which one?
Yes.
This S. This S is the gaps. Yeah. So I'll come to this. So basically, you make a list of all gaps and make one histogram. Okay. So distribution of gaps. So meaning, I'll show you on plot. You'll understand. Okay. So second one is adjacent gap ratio. The third one is it's called spectral form factor. So it's a very simple quantity. Let me just you can see my laser pointer. So it is, just look at this. So it is basically exponent of I tau em minus en. So e to the I tau em minus en. Okay. Summation mn. Okay. So here it has information of all gaps. Okay. And then average over, let's say 500 samples. This is spectral form factor. So this is now a function of only tau. Okay. So it's a function of only tau and number of eigenvalues. Is this clear? So basically it contains information of differences of all eigenvalues. Okay. So if I have just 3 eigenvalues, E1, E2, E3, this will be e to the I tau E1 minus E2 plus e to the I tau E2 minus E3, right? Plus e to the I tau E1 minus E3, okay? Plus it will have e to the I tau E1 minus E1, E2 minus E2, okay? Everything. M can be equal to n also, okay? So it's just a quantity which contains more information than just adjacent gaps. Okay, somehow I'm getting information of first and third, or 7th and 11th. Okay. Okay. So is this clear? Any question about just the quantities? 3 quantities. In this talk, I'm not going to I'm not going to show anything more. Spacing statistics, ratio, and spectral form factor. Okay, so all of you can do it. You can just take matrices, 100 by 100 Hermitian matrix on your computer. If you can code in Python or whatever, any language, and you can compute all these things. Okay. Okay. So now let me show how it looks. Okay. Okay. So before that, now we go to non-Hermitian. Okay. In non-Hermitian, my eigenvalues become complex. Typically, if you have a non-Hermitian matrix, except some special cases, take a matrix which doesn't have any hermiticity property. Okay? Some random matrix which has no connection, A dagger may not be A. Okay? Any elements can be anything they want. Then eigenvalues typically will be complex. Now, if eigenvalues are complex, things become little tricky. How do I define gap? Okay? So how do I define gap? So I have to slightly modify my I have to slightly modify my definition because now my eigenvalues will not be, let's say this is real part of the eigenvalue, this is imaginary part of eigenvalue. Before all my eigenvalues were on the real line. Now I have eigenvalues all over the place. Okay? Let me say this is the first eigenvalue. I will describe gap by the distance of the nearest eigenvalue to it. This is my S. Okay, so for this eigenvalue, this is the nearest. For this eigenvalue, this is the nearest. Okay, so if I have 100 eigenvalues, I will have 100 nearest. For every eigenvalue, there is one eigenvalue which is the nearest. Okay, now it's on the complex plane, and then from that I am going to make distribution. Is this clear?
What happens if it is in same distance? Two eigenvalues are the same distance.
Okay, that's a good question. It can happen, but then if two eigenvalues are the same distance, it's basically very unlikely because it is. Then you just you can take any of the distance, right? If there is one eigenvalue, let's say this here the way I drew it. If this is E7, then this is if this and this are same, just take that number. Yeah. Okay. Then collect all these numbers. Then collect them from different matrices, like those 500 matrices, and make histogram. Okay. Just in your computer, you can make histogram, and you can see the distribution. Okay. So what does okay? So I'll show you some plots. It will become more and more clear. So similarly, spacing ratio also becomes a bit tricky, right? If it's complex, how do I define spacing ratio? The way it is defined as, it is a distance between it's a separation between the nearest neighbor divided by next nearest neighbor. Okay, so for this eigenvalue, let's say E11. This is E. Let's say we call it E. Let me just label it by symbols. So this is A. This is B. So A minus B by, which is the next nearest neighbor? Let me call it C. So A minus B by A minus. That's it. But this is complex number. Numerator is complex, denominator is also complex. These E's are complex. And if you have a complex number, any complex number can be written as R e to the I over. So then I have my list of R, list of theta, I have to analyze it. Okay, so I have managed to define it for complex number. So till now I have not told you anything about quantum mechanics or nothing. Right? I'm just telling you how to analyze when you have complex eigenvalues. Similarly, spectral form factor also becomes little bit tricky because you cannot use this definition because tau is what here? Some real number, and EM minus EN becomes complex. Okay, so to define that, you have to define tau as T plus IS. Okay, so this tau becomes T plus IS. This tau becomes T plus IS. And then you multiply T with the real parts of eigenvalues and S with the complex imaginary. Okay, so everything is here. So all the definitions are given. So what goes into the exponent is xm minus xn times T plus ym minus yn times S. Okay, so that is how you have to adapt. So these are fairly new, as you see that even the notions of this complex spacing ratio and spectral form factors for non-Hermitian cases is a fairly new idea that they are coming up with. Okay, any doubts about this? Okay. So now let me go to Hermitian random matrix. So you can take any book on random matrices and you can see how to make this Hermitian random matrix. So n by n real symmetric matrix belongs to Gaussian orthogonal ensemble if the diagonal and the upper triangle elements are independently chosen from this distribution. Okay, so you take some number from the Gaussian distribution. Okay, so you take you draw some numbers from a Gaussian distribution. Draw the diagonal elements of a matrix from a Gaussian distribution in this form, and off diagonal elements with this form. Okay, so you just with some Gaussian distribution you pick elements and prepare your Hermitian random matrix. Okay, okay. So and this is Gaussian orthogonal ensemble. But if you have n by n Hermitian matrix is said to be Gaussian unitary ensemble if diagonal and upper triangle elements are independently chosen from this distribution. So you don't have to worry about exactly how to make this, but Gaussian unitary ensemble is when you have Hermitian matrix, but entries can be complex, right? I mean, entries can be complex, but it should just satisfy Hermiticity condition. Okay. Once it satisfies Hermiticity condition, eigenvalues are real. You can have a matrix whose elements itself are real. Right? If the elements are real, then the eigenvalues are not necessary. If elements of matrix are real, then eigenvalues can again be real or complex, right? So, but let's say that you have a matrix which is Hermitian. Okay. And eigenvalues are real. Okay, so is that clear? Okay. Now you will start making your random matrices. These are random matrices, right? So you just decide. You say I will make 10 by 10 matrices, 10 cross 10, and each element I will draw according to this distribution, and I will prepare the first random matrix. Then I will prepare second, third. I will make 500 as random matrices, and I will analyze them. Okay. I hope everyone is following till now. So now if you do this Hermitian random matrix, how does all these quantities I described look? Okay, that is the thing. So this is how it would look. So don't worry about too much difference between GOE and GUE. Just think of it as just Hermitian random matrices with real eigenvalues. Okay, that detail at this moment you don't need to worry. So you can even focus on let's focus on the top row. Okay. Forget about the bottom row. Top row distribution is this. Okay. Now, if you see this distribution, what can you say? First, just this plot. If you see this distribution, what can you say? What is P of S as S goes to 0? 0. What does that mean? That the probability of finding eigenvalues. Sorry? Yes. So the probability of finding two eigenvalues with the same value is 0. So what does that mean? That means that eigenvalues don't like to be too close to each other. That is called eigenvalue repulsion. Okay. So this basically says that eigenvalues don't like to be close to each other. Okay, so that means that random matrix eigenvalues coming from a random matrix theory, they are correlated in such a way that they don't like to be too close to each other. Okay, so that you can just by looking at this you can say. So that answers your question, like what exactly is the meaning of this? Okay, and then there is some optimal value where eigenvalues like to maintain that much distance. Okay, and then far from each other also. That's where it goes. Okay, so that is the first quantity. Second quantity is a little more complicated, but this quantity is very well studied. This is the adjacent gap ratio, right? The minima by maxima thing that I was telling about. So that has some features. But important thing is there also this adjacent gap ratio also goes to 0 as R goes to 0. This is a very interesting thing. This is the spectral form factor, the one I just explained. Okay, this is such that there is something called a ramp here. Okay, so what is the importance of this? See here, in some sense, this plot it tells you information about adjacent gaps, right? Eigenvalue, how much is known between eigenvalue and its closest one, right? But this quantity tells you about how is 7th eigenvalue with 25th eigenvalue. Because in this summation, Em minus En, n can be 7, n can be 25. So it contains all kinds of correlations. That's also important. Not just nearest neighbor or nearest neighbor ratio, not just that. It's important to contain, get information on all kinds of correlations. And if you do that, actually there is a regime, a very well-known regime called a ramp. This is a ramp. It goes linearly in tau. So this is the ramp, which is called ramp of random matrices. Very universal feature. So these are all. So important thing is these are all universal features. Like I'll show you that this kind of thing will start coming up in quantum mechanics. You know. So the important thing is the fact that there's a ramp like this. Okay. This is the spectral form factor ramp. Clear? So can someone tell me very large tau values will capture what kind of correlations? See, when I have something like exponent of Em minus En times tau, if tau is extremely large, then Em minus En has to be extremely small, otherwise it will become highly oscillated, right? So very large tau will capture the physics or mathematics of very close eigenvalues. Very small tau will capture very far eigenvalues. And intermediate values of tau will capture eigenvalues which are neither far nor near, and that regime is got by this ramp. Okay, so that is the bottom row you don't have to worry. It is similar, and there are some differences, but let's not worry about it. And by the way, how it goes to zero here, shape of this ramp, everything is known. So, but I will skip that. But okay, so same with now non-Hermitian random matrices. Non-Hermitian random matrices, also you can draw elements from some Gaussian distribution. Okay, you just draw it from some you are given some distribution with some mean and variance. You draw some elements from that and make your random matrix. But now you don't even have to worry about hermiticity. See, in the other case, if I make in the Hermitian case, if I make, let me call that matrix M. If I make the first and third element, first row and third, M1 3, that means I've already made M3 1 also, because it's hermiticity condition. I have to impose that. So in some sense, I have to only draw for diagonal and upper triangular. Then lower triangular is fixed in the Hermitian case. In the non-Hermitian, there is no this thing. So I will make this, and there are some other categories of that, but we will not worry about it. So imagine you just take a 100 by 100 matrix. You take elements from some distribution. You don't care whether the matrix is Hermitian or not. Okay. So the most general is called Geneva unitary. It's called Geneva unitary ensemble. Okay, so what happens is that suppose I draw this. Okay, let's say I draw I make 100 by 100 non-Hermitian random matrix. How many eigenvalues will I have? 100. Now let's say I have 500 such matrices. Totally I will have 100 times 500. So 100 times 500 will be 5 into 10 to the power 4 complex numbers. Now let's say I just keep on plotting these complex numbers. You all know you can just plot, right? I have this many complex numbers I plot. What is the shape the complex numbers will take? If I have this huge number of complex numbers, I will keep on plotting them. What will the shape they will take? Will they be square, circle, or will they be the middle? Okay, let's say circle, but will the more eigenvalues be at the center or in the edge? Okay, so this is a very interesting exercise for this random matrix. After the talk, if somebody is interested, I can tell more details how to make this. It turns out that it forms a uniform disk. Okay, eigenvalues are such that they will just form a uniform disk. Okay, so it will be just uniformly spaced eigenvalues. Okay, but you have to do it. Okay, but it's very interesting because it's hard to say, right? I mean, it could have been in the middle. There could have been. It could have been like a cap. Right? If I see density of eigenvalues, if they are more in the middle, then it will be like a cap. If they are more in the edge, it will be like a bound. But it's neither. It's like a flat disk. Okay. Okay. So in the Hermitian case, can you guess how it will be? Hermitian case, the eigenvalues are real. So then if I plot, this is real, let me just call it x. This is density of eigenvalues, rho of x. How will it be? Huh? No. The eigenvalues will lie on the axis. Eigenvalues will, suppose I want to make a density of them. Eigenvalues will lie on the real axis. Like it's like let's say people are all standing in this line, but if there are more people at the center and less people at the edges, what is the density of people?
Poisson distribution. Gaussian distribution.
Okay, so it turns out that in the limit of large eigenvalues, okay, or limit of large numbers, it turns out that it is actually semicircular. It's square root of 1 minus x square. Okay? Okay, you have to do it. I mean, there are ways to prove it, but you would think naively it should be Gaussian or something like. You would think that there should be more at the center, and there are more at the center. There are more at the center, but it actually takes semicircular.
But the entries we have taken from the Gaussian distribution.
Very good. This is an excellent question. That is the beauty of random matrix theory. Entries have taken from Gaussian distribution. You have made the matrix elements from Gaussian distribution. Okay, and entries are independently taken. Okay, so the matrix elements are independently chosen, but the eigenvalues become correlated, and they actually form a semicircle. Yes, that's a very good question. So, question was, even you can ask the same question even for non-Hermitian case. You can say, why am I saying disk? When I said everything is taken from Gaussian distribution, why should the eigenvalues become a disk? But it does. Okay? Yeah. So all these things I'm saying is you can in half an hour it will take half an hour or even less than that to get the semicircle. Okay? If you have Mathematica or Python or C or Fortran, anything, it will take half an hour. Okay? So that's clear? Okay. So again with this, again let's see the top row. Okay, don't worry about the bottom row, it's another kind of this thing. Top row, again there is level repulsion. You see that as S goes to 0, it's even more hesitant. If you see, this is like even like this. Okay, it is S cube actually. It goes to 0 as S cube, and this is how this adjacent gap ratio plot will look. Scatter plot of. Remember this quantity? I had written this numerator by denominator, and this is how it will look. And the spectral form factor has some properties. And here also you have a ramp, but this is a different kind of non-Hermitian random matrix ramp. The first ramp I spoke about is a linear ramp, T. Okay, it goes as tau. I call it tau. Here it is a non-linear ramp. Okay, but these are some properties of non-Hermitian random matrices. Juniper. Juniper. No. Juniper is the name of the person. These are Juniper ensembles of matrices, and that's why GIN is the abbreviation actually of Juniper, and O is orthogonal ensemble. And yeah, just like you have GOE and GUE. Yeah. Okay, so it's clear. Okay, so you can really do this. It's really simple. Okay, it's a lot of fun. Okay, because of precisely that point that that you may think that you're taking everything independently, but you see it's very interesting, right? You may be taking n square numbers independently, but from n square numbers. So what is the How many elements are there in a non-Hermitian random matrix? Order n square, right? Right? N square. So let's say n square of them are uncorrelated. You just draw it from some Gaussian distribution. But out of that, how many elements are there in eigenvalue list? N, right? So from n square, you got n. So something needs to be correlated, right? If I have 100 square, which is 10,000, from 10,000 numbers, I'm getting 100 numbers by doing some. If I convert a matrix to a list of eigenvalues, I have dimensionally reduced the problem. And in the process, I have introduced correlation. Okay? So that is a rough idea, but okay, good. So this is a brief, whatever I need for random matrices, I have explained. There are some conjectures now. I will just briefly describe these conjectures. So there is one conjecture by Berry Tabor. They say that typical quantum Hamiltonians with integrable classical limit have level spacings which is distributed according to Poisson distribution. So I have spoken about random matrices, but for Poisson numbers, okay, for the Poisson process, the distribution is just something like this. It's just something like this. Okay, P of S will just go as e to the minus s. Okay, so these are not random matrices. These are just from Poisson numbers. You make a list from Poisson process. You calculate P of S. It will be e to the minus s. For random matrix theory, it was like s e to the minus s square. Okay, is that clear? So, and then there is a BGS conjecture. What they say is, so we are not really going, okay, we are going to use a bit of this also, but BGS conjecture means those Hamiltonians which have a chaotic classical limit. Okay, if a Hamiltonian has a classical limit which is chaotic, okay, then the corresponding quantum system has level spacings which are random matrix theory. So let me just explain this. So suppose you have a system, let's say some complicated quantum harmonic oscillator, which has a classical limit. Okay, if that classical model is chaotic, if a classical model is chaotic, let's say it has positive Lyapunov exponents and Poincare sections which are chaotic, then the quantum version of that has eigenvalues which are like random matrix. You see, it's a very nice correction, right? So is that at least this statement is okay? It's clear, right? So then there is this another conjecture which does this for open systems. Okay, it says that those Liouvilleans, I'll come to this, those classical systems which are integrable, their quantum systems have 2D Poisson distribution. 2D because numbers are now complex. Eigenvalues are complex in the non-Hermitian case. And those whose classical limits are chaotic, their eigenvalues are like non-Hermitian random matrix. So all you need to know from here is, if a system is chaotic, quantum chaotic, it is mostly connected to random matrix. Poisson process. Okay. So that is the thing. Is this clear? Okay. Any questions so far? Okay. So now I will come to the quantum systems. So as I said, quantum systems. Now I'm not talking about random matrix theory, just talking about quantum systems. Okay. So there are two categories. One is Hermitian, another is non-Hermitian. In Hermitian, I'm going to speak about spin chains. Okay. So don't worry if you don't understand this part, but pinches with disorder. See, in random matrix, how did I make samples? I just made more and more random matrices. But in reality, if I want to make samples, I will take the same system for different kinds of disorder. Okay, so that is the idea. But you can also define this concept for clean quantum lattices, which also I will explain. Then there are two kinds of non-Hermitian, at least two kinds of non-Hermitian systems. One kind of system is called Liouville systems, which is basically, let us say I have a quantum system, like us, all of you might have got studied quantum harmonic oscillator. Suppose I couple a quantum harmonic oscillator to an environment. So what is an environment? Environment, you can mimic it as bunch of infinite quantum harmonic oscillators. And suppose I manage to understand the role of this environment quantum harmonic oscillator, you can write, sometimes write this something called Lindblad form. Okay? Some Lindblad master equation. Okay? Some of you in the audience for sure know it, but in case you didn't know, so it's an effective equation for your system, taking into account role of environment. Okay? So, and the environment makes it non-Hermitian. Okay, I'll give you one example, but that's it. But the second kind of thing is, I don't worry too much about how this environment results in this Lindblad, but I will just take my Hamiltonian and make it non-Hermitian. How do I make a quantum harmonic oscillator non-Hermitian? So if I have a quantum harmonic oscillator like this, is everyone aware of this this kind of representation? How do I make this non-Hermitian? This is Hermitian. How do I make this non-Hermitian? Huh? Good. Yeah. So one simple way is to take this and make it omega plus I kappa. Right? This is non-Hermitian. Now, how it came, I will not worry about it at the moment. But I have taken this and I made it non-Hermitian. As soon as I make it non-Hermitian, whatever eigenvalues I get will start becoming complex. Okay? So that is the fourth category. Okay? Now, each one of them is important in its own way and actually offers different kind of benefits. Okay? Is this? Please let me know if you don't understand, because yeah.
So for all these four types, we have a classical equivalent.
That is no. That's a very good question. Usually, it's a very hard problem. You see, the problem with this conjecture is you also need to find a classical limit. That's very hard. Okay. So if I have a quantum harmonic oscillator, so if I can write this A dagger A quantum harmonic oscillator, I can write it something like x hat square plus p hat square, right? By 2m and so on. But if I forget those things, it is basically this, right? And I can remove the hat and make it classical. But that is not obvious. And many times we don't have a classical limit. So many times testing this conjecture becomes difficult because you don't have a classical limit. Okay? So
the conjecture is based from the quantum to the classical limit, or it's from the if a chaotic classical system, if it is
has quantum version.
quantized,
And
then this conjecture will apply.
Either way it can work out. Either way it can. But there are systems which don't have a classical limit. Where that's fine, it will have random matrix theory properties and so on, but you just cannot use this conjecture. That's all. I'll show you actually. Actually, one of the, first system I'll show you doesn't have a clear classical limit, but that's okay. Verifying this conjecture is not the main thing for what I'm speaking. But I just said that classical chaos is itself a very interesting topic. So because I'm going to speak about quantum chaos, I wanted to just make a comment that if there's a classical version of any of the systems I'm going to speak, its classical chaos itself is a very interesting non-linear. It's a non-linear system, sometimes with drive and dissipation. Without even getting into quantum mechanics, that itself is an interesting thing to ask. Lyapunov exponents and so on. So that's what I wanted to. Okay. So Okay, so first system I'm going to speak about is called disordered spin chain. So these things I will not. So these things I already explained what it is. So don't worry about this. So so now in this disordered spin chains, if I increase the disorder, it starts becoming more and more localized. Okay, which means less and less chaotic. Okay, so that is the disordered Hamiltonian, and this is my spectral form factor which had this ramp. But if it is localized, we derived another formula which doesn't have a ramp but which is another function. Okay, from just by using Poisson processes. Okay, so the answer is so maybe I will skip the derivation of this, but let me just go to the answer here because I have 10 minutes. So I will accelerate and then slow down again later. So okay, so disordered Hamiltonian. So this is a spin chain, quantum spin chain with disorder. Okay, and the disorder is here. This omega I uniform distribution minus W to W. So from -1 to 1, take a random number and call it omega I. Okay, and make your entire spin chain, and then make a 500 such Hamiltonian. Okay, and then diagonalize the Hamiltonian. These are all Hermitian Hamiltonians. They will all have real eigenvalues. Now this has, I mean, directly if you see this, there is no reason why this should be connected to random matrix theory, right? This is just quantum system which has eigenvalues. But it turns out that for low disorder, you will get perfect agreement with this ramp. And for high disorder, you will lose the ramp. And you will get this 1 over tau square behavior will be found out. Okay? So question is, I have a complicated quantum disorder system. How do I classify its chaotic or non-chaotic features? Especially when I don't have a classical limit. I mean, there's no clear classical limit for this. Okay? So if I don't have a classical limit, how do I even start asking the question whether the system is chaotic or non-chaotic? So that is why we try to analyze its eigenvalues and ask whether these eigenvalues fall into random matrix theory. Okay? And if they don't, random matrix theory P of S, how did it look? It went like this, right? But if it is Poisson, it will be just like this. So in this case, it actually goes like this. So that is the connection of this spin chains to random matrix theory. Okay? Any questions? Now, the second equation actually has a classical limit. Okay, this is the second model, which is a large spin system. This is called Tavis-Cummings lattice. It is a large spin coupled to a harmonic oscillator. Okay, so it is this part you all know. It's like a bunch of harmonic oscillators. Now each harmonic oscillator is coupled to a large spin. Okay, and this is the Hamiltonian. It is on a lattice. Okay, the way to take a classical Hamiltonian is you take S and make it a vector. Okay, so you make S a vector, and this A you make it in terms of X and P. So you have X, P, and S vector. Okay, classical system, and so on. So it's a classical limit, but I'm not going to speak about the classical limit. I'm going to stick to the quantum system. Okay, but and we'll ask what are the eigenvalues statistics for this. No, till now it's closed. Previous also is closed. This is also closed.
Just interaction.
Huh?
Just the interaction.
Just the interaction. No non-Hermitism. Everything is real. All eigenvalues are real. Yeah.
Non-solvable.
Huh?
Non-solvable.
This is also no. So this lattice is non-solvable, but just one unit is integrable. Yeah. But this is a very interesting question. Actually, this if this is you have a lattice, because you have a lattice, because of this J, look what J is doing. Different harmonic oscillators. Okay, if I cut off J, it will actually be disconnected units. And actually each unit is not random matrix theory. Okay, so it is the J which causes chaos, which manifests itself in terms of eigenvalues behaving like eigenvalues of a random matrix. If you cut off J and calculate eigenvalues, they will behave like eigenvalues as if it was a Poisson process. Okay, so that's a very important point. Yeah.
So this model is just in theoretical model, or it has in any physical equivalence?
Okay.
Because, I got this question because usually the process is we have a classical system, we have an Hamiltonian, and from that Hamiltonian we construct that quantum mechanical part. So here you are just defining an Hamiltonian which is inherently quantum.
Yes. Yes.
So, because if it doesn't have a classical counterpart, then is it a realistic?
Yeah. So there is one version of that which so this is A dagger S minus plus A S plus. Okay. Suppose I add two more terms like A dagger S plus and plus A S minus. Okay. Then I can write this Hamiltonian as A plus A dagger times Sx. Okay. And this Hamiltonian is called the decay Hamiltonian, and this is actually realized in experiments. Okay, so this particular lattice is not yet realized to the best of my knowledge, but people are getting close. But to answer your question, it is like coming actually very much from quantum side actually, by mimicking this large spin as a bunch of small spins. I can tell you the story, but it's coming from a actual quantum system. Okay. Okay, so now last few minutes okay, so now let us first is creating connections to random matrix, and it turns out that it beautifully agrees. So the J is large. J is 1.0. Okay, you see the eigenvalues perfectly agree with Gaussian random matrices. But when J is small, meaning that this thing is still barely connected, and it starts remembering that when it was alone, it was Poisson process, and this J is not really good enough. Its spectral statistics actually is okay. So very nicely eigenvalues behave as either Poisson numbers or random matrices. And okay, this we very nicely capture both the ramp when J is large and this 1 over tau square when J is small. And this gap ratio, okay, I will skip this point. It's okay. It's average of that gap I defined, but basically this gap ratio itself behaves differently in the two regions. Here the tuning parameter is actually J. When I ramp up J, I make it more and more chaotic. Okay. Okay. So now this is the model that has been realized. Okay. This is a decay model. Okay. Okay. So color has changed, but this is okay. So here it's an open system. Okay, this is the first open system I am speaking about. This Hamiltonian is a Hermitian Hamiltonian, but in actual typical A is something or this cavity is made of some effective cavity, has some dissipation, and that is incorporated by this L operator. This is a Lindlardian, okay, and basically this and this makes it a non-Hermitian system. So I'm assuming that many of you may not be familiar with. Think of it as effective non-Hermitian description, okay? And we are going to analyze the corresponding non-Hermitian matrix describing this open quantum system, okay? So effective for those who are familiar with this, I just write one thing and you immediately see what I mean. Okay. Basically, the whole density matrix of your system, okay, can be written as L of rho. Okay. This L will be a non-Hermitian, big non-Hermitian matrix. And this non-Hermitian matrix eigenvalues you will analyze. Okay, that's the rough picture. And if you do that, you will see that when lambda is small, it actually agrees with 2D Poisson. Okay, 2D Poisson is different from 1D Poisson. Okay, and when lambda is large, this is the lambda, it agrees with Geneva. But one very interesting thing about 2D Poisson is, if you take, you can make 2D Poisson numbers easily. Okay, for making Poisson numbers, you don't even have to think of matrix, right? You just, draw numbers independently and make a list of them. But if you make a 2D Poisson, the distribution in the complex plane can, if you choose carefully, the distribution may still look like a disk. The Juniper also looks like a disk. Okay, so, but just because things look like a disk doesn't mean their gap is the same. That's a very important point. Okay, so how eigenvalues look, that eigenvalue cloud of eigenvalues just look for you, doesn't mean that you can guess how is the gap distribution. Okay? Because think about it, right? I mean, if I have a uniform disk and I just throw numbers inside the disk randomly, like Poisson numbers, complex numbers, and I have a disk. But it's very different from correlated eigenvalues coming from a random matrix. Okay, so that is a very important point. Usually there is a confusion that if it looks same, then probably it has similar, but these features are very fine features. They are very hidden. Okay. So then, in fact, this is how the eigenvalues look. This is the first time I'm showing some other kind of plot. This is how imaginary and this is how the eigenvalues look in the complex plane for this decay model, open decay model. Okay, but this is something which is, this is an example where the eigenvalues don't look like a disk at all. Look how the eigenvalues are arranged. But their level spacing, okay, it looks like this. So only focus on lambda equal to 1. Level spacing looks like Juniper, but how it actually looks is nowhere near a disk. Okay, so I'll skip these things. So I'll speak about the last. Can I have 5 minutes? 5 minutes. Okay, so just this last part. This is the part where this is okay, where I don't think of Lindblad and things like that. I literally take my Hamiltonian and I just make some parameter complex. Okay, so this is what I do. So here you see, before if I have just HI NI, I will put an I gamma. Okay, like I kappa, I'll put an I gamma. Okay, so these are different kinds of models where here you can put non-hermiticity in one way. This is a different kind of non-hermiticity. Remember, I have J, if I have J A1 dagger A2, but imagine I have J prime A2 dagger A1. Then also I make it, suppose I have a term which is like this. Okay? Usually we just write this plus Hermitian conjugate. But Hermitian conjugate is what? J A2 dagger A1. But let's say I want to slightly destroy it. Okay? What if I put e to the g here and e to the minus g? Now, is it Hermitian when g is 0? Yes? Is it Hermitian when g is 1? No, because this is e to the 1 and this is e to the minus 1. Is it Hermitian when g is equal to I? Okay, so what I'm saying is that this g is good enough candidate to break Hermitian. Okay, and if I take g equal to 2, then it's clearly, so this is something I'm doing here. I literally put e to the g and e to the minus g. Okay, but okay, so I will these are distributions of that gaps, okay, that I'm plotting here. But let us, okay, so in the first two models I'm showing that if you increase the disorder, you will actually go towards Poisson, but for low disorder, you will actually go to random matrix result. This is the random matrix theory result. and here is also random matrix theory result. And one point here is if the underlying Hamiltonian has some other symmetry, okay, some special symmetry, it is still non-Hermitian, but it has some symmetry. Then you have to compare it with non-Hermitian systems with that symmetry. So what is an example? Suppose that A is not equal to A diagonal. So it is non-Hermitian. But let's say A is equal to A transpose. Okay, so if A is A transpose, still eigenvalues can be complex. Okay, but then I have to compare it with those non-Hermitian matrices which have this extra symmetry. So anyway, so that is so we try to there's a new symmetry class in addition to this Juniper class which is called AI dagger class, but don't worry about it. And this is another model, and this is a long range model. So this is a model in which most of the models, all the models I told till now, it's coupled to its neighbor, A1 dagger A2, A3 dagger A4. Okay, but here this can couple to this and so on. So when you have not only interaction and disorders but long range, then we find that if I increase the range or couple to many people, then I start getting closer results to random matrix theory. Okay, so with that, and then you can compute dissipative spectral form factors and so on. But this is basically shows resemblance with non-Hermitian random matrices. Okay, so conclusions are that I discussed some properties of Hermitian and non-Hermitian random matrices. Just few properties: spacing statistics, spacing ratios, spectral form factor. We discussed quantum Hamiltonians, both Hermitian and non-Hermitian, and we discussed mainly chaotic behavior, but also regular behavior or localized or Poisson kind of behavior. And outlook is actually one of the things that you are asking. In fact, is our outlook. We are still working on this. Some of our models are suitable to study this classical quantum conjecture, but still there are a lot of open questions. It is not at all clear how to test these conjectures. Okay, and whether there are other diagnostics that can provide chaos, and there are other models like quasi-periodic systems and Fouquet systems that we are also studying. I hope some of it was at least clear. So thanks for your attention.
No, the seminar is open for discussion.
Sir, the plot where you pointed the points on the disk,
Yes.
what is the minimum points on the positive side of it?
Oh, very nice. Good. So you see this one. Okay, so this is actually coming from Hamiltonian. Okay, actually what happens is this is a disk of not eigenvalues. This is a disk of these ratios. This ratio, adjacent gap ratio, it's a disk of that. And what happens in that disk is, if it is random matrix theory, actually it will look like a disk. Sorry. So if it is a random matrix theory, non-Hermitian random matrix theory, actually that disk is like this. Okay, this is a disk of Z is not a uniform disk. Disk of eigenvalues is a uniform disk. Disk of Z is not a uniform disk. Okay. Similarly, the disk of for Poisson process, disk of Z is actually uniform. Okay. So eigenvalue disk may be uniform both places, but Z disk is different. Okay. So for some reason, what happens is that adjacent gap ratio disk has some missing points here, and that is sign of some correlations of that. Yeah. So these are So that is the
So that's the missing correlations in the original random matrix.
Yes. In fact, what does that say is the following, right? So let's say this is a disk. Okay, this is disk of Z. Okay, but what is Z? Z I told you is R into the I theta, right? Okay. Now you see from here, if I want to calculate average of cos theta, because of this asymmetry, it will have some value. If it was a uniform disk, average of cos theta would be 0. Okay, so in fact, this basically tells you what is the average of R and cos theta. Yeah. Yeah, this is it. So many times, instead of seeing the whole distribution or seeing this, it's very nice to see these things, but one should extract even one quantity, like give me average of R. Forget about this whole disk and all. If this whole disk can be written as Z equal to R into the I theta, and there are some 10,000 values of Z, just give me average of R and give me average of cos theta. And what is this number for a random matrix theory? And that number is known. And actually that number matches quite well with quantum Hamiltonians. That is the, yeah.
Another thing is, so how you get your inspiration for modeling this kind of Hamiltonian? Because we are lacking a classical form.
But that is so many Hamiltonians. We start from thinking of actual quantum systems, motivated by cold atomic systems, ions, or condensed matter systems. Many times you start with the quantum spin chain, and so many times you actually start with the quantum from the quantum side actually many times, and that's how we start. Yeah.
You hear the question? We have further discussion.
Thank you so much for the
Thanks.
amazing talk, sir.
Thanks.
Thank you so much for your patience and listening. Tea is being served below. Please take it. Thank you.